Hey everyone, I hope that you can hear me all right. I'm new to this, so I'm going to be figuring out not just Raspberry Pi Pico today, but also how to do live stream stuff, so hopefully this goes out all right. I got the chat up on the side of my screen, so I'll try to pay attention to that as we go along. I guess, all right, so I've got this little screen up here, which is the Pico. It's a very high quality picture of it. I can hear. I think I can hear you back through. All right. So I'm using this for a few projects right now that are going to be put on some circuit boards, and I realized that I should probably understand how these things work before I start doing that. So that's what I'm going to try to do today. I know that you can use. Let's see. You can use Python or C or a handful of other things, and I haven't decided which I want to go with yet. So I'm just going to try to get a quick hello world going before I do anything else. I hope I don't need drivers for this. Alright, so... Yes. What do I need? Man, this is like a tutorial written for kids, maybe. Alright, I've got pins soldered onto mine. Oh, you know what? I just realized I'm probably blocking everything. There we go. Move this out of the way. I'm just looking at the Raspberry Pi project's website right now. Yeah, they're saying put a breadboard on it. Here we go. I want to plug into the USB port. Install Thani. I guess I'll just do exactly what they say first before I do anything else. Make sure I have the latest version. Let's do this for Mac. Thani.org. I guess I'll plug myself in here. Have a cable somewhere.
So this is the other one. I don't know if there's anything we want to look at here. This is mostly by...
Man, I am running out of USB ports today. Which one is going to go?
Yeah, so 2021, in 1 month we had 400 million.
Got docking stations galore here.
485. So I think that 4.7 billion is accurate. Yeah, just from the other one.
Alrighty.
Yeah.
I don't know if there's supposed to be a light, but I'm not getting any lights on here. I'll just assume that everything is fine and not freak out quite yet. Put this in here.
For chassis?
Alright. Thani, Python. Alright, so I guess I'm learning Python for this, or learning how to do Python on this. Let's download this for Mac. I think that was from earlier. Yeah, we'll install this. While that's running, let's go see what we have to do. Wow, this looks like just an interpreter window here. This reminds me of the Arduino framework quite a bit. Or processing even. Alright, let's launch that. Wow, is this really all we're gonna do? Okay. Thani. Oh, I get it. It's like Python. Thani.
Yeah.
Oh, there's a picture in the background. Yeah, we've got a bunch of like famous people drinking water paintings around the building here.
That I should be able to.
All right. So it looks like you just do print hello world. This is going to be weird if this all just works. I don't know if there's something special on the Pico that's going to kind of like process this, but let's try with double quotes too. Already deviating. Okay, I get the exclamation point in here. And then I'm gonna do exactly what this says. Oh, and there we go. Yep, so we're all excited. We added one line of code and we gotta change this. If you've never used it before, you will need to add the MicroPython firmware. Okay, so that would be the part that actually interprets stuff. Find the boot select. It's an easy button. Press it and hold it while we connect the other end of the micro USB cable to the computer. Wow. Alright, so I gotta unplug this, press the button, and then plug it in, it sounds like.
Oh yeah, for sure.
Raspberry Pi is shown. Alright, so we're not using another Raspberry Pi, I'm using my computer.
Yeah, and
In the bottom right hand corner we should see a version of Python that we're currently using. What are we using?
Let me make sure that
Python 3.7.9, okay. In the bottom right hand corner, click on the Python version and choose MicroPython. Oh, so we gotta change it.
So this looks correct.
Sure. Try that again. There we go, MicroPython. Here you can install or update. Alright, so this is going to do the firmware right from here. This is kind of sweet. Oh, does this show up as like a removable drive or something? Oh, I just saw it. It was right in here, right in my removable drive section. It says it's done. Volumes RPi2. Wonder if it's going to show back up in here. Alright, close that. Is this running? Is that it? Is that all I had to do?
Do you want me to this?
Yep, I did that. So now I use the shell. Oh, okay. So look at the shell. So this is, oh, I can type commands directly into the shell. This will be cool. So I guess this doesn't really matter. I probably was trying to test Python originally, so I'm guessing that this is running right on the Raspberry Pi Pico. So if I type in print Mitch is back, then
yeah, I can export it. Yeah.
Okay. I guess that makes sense. I wouldn't really be able to tell if that's running from my computer or if it's coming from the Raspberry Pi, but I'll just assume it's coming from the Pi. Adds hardware-specific modules such as machine that you can use to program the Pico. Alright, so from machine import pins. I guess everything in this is going to be that magic machine option here. So let's do from machine import pin. Okay, that didn't throw an error. You know, can I just... I don't want to keep typing this in here because that's probably dangerous. This is going to be live most likely, and anything I do is going to be executed as I type it in. So let's see if I can do it up here and then just keep pushing it to the Pico. Can I just like hit this, run current script, Raspberry Pi Pico? I don't understand all the magic behind this, but I'll probably figure that out later. How does this work? File name? Do I just hit OK? Oh, you need to select a file. Mitch. Okay, does that work?
Yeah, do you want to... Well,
okay, I think I just lost all of my formatting in here. I'm going to try to save this as a different file and see if I can get my formatting back in. Oh! I just saved this to the Pico. I think. Okay. Hello.py, if I do that. Yeah, see now because I did the Python extension, I'm getting my text back. Okay.
This is the breakdown.
We've got our LED. I'm going to just go like this. There we go. That's much better. That is almost better.
And then these numbers at the right are, I believe, what
Can we read that? We can almost read that. Let's make this a little bit different. Oh, hold on. I've got a fantastic idea. Check this out. Can I move my fate? No, that was a bad idea. Okay, we'll just leave this. So we're gonna go LED equals pin 25. I don't know what that is. And then it looks like we have pin dot out. So we got some more magic going on here. So I guess we're creating an LED object, and that object is a pin object. So I guess this is some magic thing where I can then type in LED dot value, which I'm assuming will set the value to 1. So let's see. Run current script.
That should be helpful as well.
Look at that. Look at that. We've got an LED. All right. I don't know how to add delays yet, but can I write a 0 to it and push it back? Oh, there we go. All right, so we're turning the LED on and off. That's about as hello world as we can get. Oh, thank you for the STM series. I'm going to be getting back to the STM series, actually. I've got a project on hold here, but I'm going to probably pick back up with like SPI or something like that. That was kind of one of the things that delayed everything, and then I realized it's taking longer than expected, so I'm just going to jump back into things for that. Anyway, we should see, yes, we did. Oh, look at that. We're ahead of the game here. LED value to turn it off. Cool. Blink the onboard LED. So we've got our toggle. So let's do LED dot toggle. This doesn't take any arguments. So if I run this, the LED is on. If we look at our big screen up here, and then if I hit it again, so every time I run this code, it reruns it, turns it on and off. Okay, cool. That's cool. Toggle is nice. That's convenient. I don't remember if there's anything like that in Arduino.
Both of these?
Oh, look at that. Click run, enter blink.py. Tip, you need to enter this so it recognizes it as a, yeah, so you got to put in .py for it to recognize a Python file. You can save your program to your Raspberry Pi and run it. So I still don't see the Raspberry Pi Pico as like an object. If I were to plug something in here, I'd see it as like a removable drive over here, but I don't see that on my computer, so it's not acting like a mass storage device, which a lot of like ST Nucleo boards will do that. They'll act like a storage drive, and you can drag and drop files to it. So I'm not sure how it's transferring the files over here. Here we go. So now we're getting the timer module. So it looks like timer is part of machine. So I think machine is everything that the Raspberry Pi Foundation, I guess, came up with on their own. I'm going to just do it like this. I'm going to do something a little bit different. I'm not super well versed in Python, but I think I understand enough of it.
This one?
All right, so we'll import timer as well. So now I should be able to put, in the same way that I called pin here, I should be able to do timer as well. So they're creating the pin, and then they're creating a timer. So I'll follow their same suit. We'll create a timer here, which is going to be called, so we're calling ours timer. And you know, sometimes I like to, whenever I'm not sure what, so like, whenever I'm not sure if this is what it has to be called timer or this is what has to be called timer, I'll just like put my name in it somewhere. I do that a lot. So we'll have Mitch timer equals timer. And now we'll do def blink timer. So they're creating a function called blink, which is going to toggle the LED. Okay, so this is how timers are working. This is kind of, it reminds me of JavaScript almost a little bit with like a callback method. So we're going to initialize the timer. It looks like specifying frequency of 2.5, probably seconds. Mode is timer.periodic, so I'm assuming that means it's going to keep happening. And then here's our callback method. So every time that this timer fires, it's going to call this blink object. Okay, that's pretty different from how like Arduino and stuff works and how delay works, but it's kind of it's more asynchronous. All right, bud.
Calipers.
All right. So let's give this a shot. So we're gonna have to create a thing here, and I'm gonna call this Mitch blank, because I like to know if it's something I can do. It looks like it takes in a timer object. So that will be, I guess, an object that we could answer we could use later, I guess. So LED.toggle, so we've already got this. This is nothing new. I'm just gonna get rid of our LED.toggle here. So anytime that this Mitch blink gets called, we should get a toggle. All right, so let's get this timer to init. Mitch timer dot init. So in Python and like C and stuff, you usually have like a prototype. So you might have, in this case, there's 1, 2, 3 variables. So like in C, we would typically do something like 2.5 comma, I don't know, periodic comma blank or something like that. But if you're not familiar with Python, you can directly set variables themselves. So like they might not be actually defined in this order from the actual prototype, and there actually might be more arguments that you can pass into this. So it's pretty typical to explicitly say freak equals 2.5, mode equals timer.periodic, and then callback equals blank. So that kind of lets you explicitly call which variables you want to set, and then if you don't call them, they'll typically result in some like default value. So I'll probably see what ones of these I can remove as soon as I'm done. All right, if I have no problems, nope, looks like I do have a compile error. Blank is not defined. See, this is why I do this stuff. So callback equals blank, that doesn't exist because we want to call Mitch blank over here. So I want to call this function here. So Mitch blank, and
so
save
you want
that.
this for both as well.
All right, well, it looks like I've got a bunch of stuff on my other screen. It looks like our LED is blinking. I don't know what this 2.5 is, but it certainly doesn't look like 2.5 seconds, which is interesting. Huh, I wonder what that means. 2.5 seconds. Is that 2.5 times per second? Is that what that means? Is this times per second? If I do 1, will that be once per second? Is that slower? Oh, it is. Look at that. Okay, so frequency is times per second. So if I do 10, is it going to blink really fast? There we go. Now we're getting it to blink faster. That's cool. Alrighty. Use digital inputs and outputs. So I guess I can go grab a resistor if I need to, and a LED. Let me see. This is all timers. I don't doubt that I can do this. This looks exactly the same. They're just using a different pin number. Pin number 15. So how are these things marked? They're not marked at all. Okay, that's cool. So there's not like, I can't see. I don't know if I can hold that up. It's going to be blurry. But they're not like drawn out on the sides of here. There's no writing or text or anything. So I'll probably have to pull up a pin diagram or something like that if I'm going to learn how this works.
No, I don't have that to
shrink that back down. Did they give us a pin diagram here? Wouldn't surprise me if they did somewhere on this page. Okay, no they don't. So let's see. Raspberry Pi Pico pin diagram. Sure, we'll use this one. Okay, zooming in doesn't work. Open image and new tab. Let's just go right to the image. Wow, that's big. That's a big image.
I have these, and I have.
All right, so yeah, I guess I'll just follow suit until I feel comfortable. I'll go grab an LED. Maybe this is a good time. I've got this box of old parts I've ripped off of previous projects. Look at that. There's an LED in here. Got an LED. Cool. So I'm gonna hook this up. I think the long pin is power. So I'm just gonna pick. I don't know. We'll do this.
Yeah. I don't.
Does it matter what number I choose? Probably not.
I mean, there's this.
So I think GP is probably what we're going to reference it as. So here's UART. I don't want to touch those. I don't know. I'll just do
I think I have that here.
GP. That's UART 0. What? Wait. There's 2 UART 0s? 2. Are these the same pins? You know, all right, I'm just going to do GP 0. Let's do this. So I'll hook up the positive pin to GP 0. And the negative pin will just kind of go to an empty slot right up above it. Man, I wish I had a better camera for this. Yeah, it's going from the GP0 pin, which is
I
man,
think so.
I'm bad
So
at
do you
this.
still want this?
the long end of the LED is plugged into this pin, and then the other end is just kind of like above it in an empty spot on the breadboard, not connected to anything else. And now I need to use a resistor and tie that down the ground. So let's see, do I have resistors in here? I do not. Let me go run and grab a resistor. That should work.
There may be a way to get more granular with it, but I don't know how. Oh, right. I already.
All right, I got a 330 ohm resistor. I just have like packs of generic resistors laying around, so I'm gonna tie this from the other end of the LED. Oh man, this is gonna be fun. I gotta go from, uh-oh, did I stop the light from blinking? What did I do? I gotta go down to a ground pin. I should probably not be messing with this while it's plugged in. Oh well. Okay, so third pin down is ground. So I gotta go from the other end of the LED down to ground. Okay, so I don't know, this isn't really a reset pin. Is my code still working? Back end terminated or disconnected. Uh-oh. Stop, restart back end. What did I do? Run. Okay, well it's back up and blinking again. So now theoretically if I change 25 to probably 0, GP 0, that should be my new LED. So let's see if that makes that blink. It does. So now we got this red light blinking. Cool. Can I make this also print something too? Print blinking. Is that all we have to do? Let's run that and see if I get this. No, so it's not quite as simple. I think this must be like maybe a local thing on here. So it's not like I can't see that over UART, maybe. Try one more time.
Cool.
Yeah, no, I don't see anything here. Uh-oh. What happened? Expected, got blinking, got something blink. Yeah, okay, well, that's bad. We'll not do that. Let's put this back on here. Cool. Device is busy. What have I done to this thing?
This is
Can I set this frequency back to 1? Okay, I think I've made this pretty angry.
Yeah, no problem.
Stop / restart backend. I'm just gonna hit that. I don't know what this does. I'm gonna hit play. Let's see if my light blinks once per second. There we go. We're back to, it's blinking once per second on here. Maybe something was just wonky. I'm gonna try this. Print hello. And run it. There we go. All right, so it is printing hello. So wow, all right, so that's serial just is that easy. That's cool. Wow, that was pretty self-explanatory. I wonder how fast this thing is running. I didn't have to do any like serial.begin or serial anything. This is nice. All right, I'm gonna breeze through the rest of this getting started thing. I'm probably not gonna do all of it. I'm just gonna see if anything looks abnormal. So there's blinking an LED, getting a button. So I'm not gonna worry with inputs, but it looks like there's another button object here, which you can say if it's pin.in or pin.out. So we'll have an input pin if it was a button. And it looks like it's got a pull down resistor built in, which is really cool. So that way the pin's not floating. And then if button.value, so that probably returns a 0 or a 1. Oops, 0 or a 1. So if it probably is a 1 if it's high, because that's how they wired it up. It looks like, yeah, the other end of the button is going up to the high voltage side, and when it's idle, it's being pulled down. So they're using like kind of like the inverse of what I usually see a lot of people do. Usually when you press a button, you pull it down to ground, but they're probably doing that to make this make a little bit more sense. If it's high, then it triggers something. Okay, cool. PWM, I'm not gonna worry about this much, but it looks like there's another item called PWM that we can import in the same way that we had a pin object. So actually it looks like it takes in one argument to create, which is a pin object. That's cool. You can just set the frequency. Okay, I'm not gonna touch any of this stuff. So now I have to make the decision of, do I want to work on this in C or MicroPython? Because this was pretty straightforward to do in MicroPython. In terms of performance, that's a different story. But what I kind of want to do is, my plan is, so I got like, somewhere in my drawer over here, I have a bunch of RP Picos. I have lost the RP Picos. I'll be right back.
No.
I thought I saw a candidate.
Okay, I got it. So I've got the little strands here. I got these from Adafruit a little while ago. Before they announced that you can get them in bulk, so I just got these little strips of, like, I don't know. They come in 10 packs, so they're 2 strips of 5. And I guess I'll pull one out here. So this is really the magic. That little thing. It's upside down. The back side is just that. So I'm designing a board for this to go on, and I really don't know what the minimalist design is for this, so we'll see what it is. From what I've read so far, is those chips don't have any onboard memory, so like all this stuff that we're pushing onto it right now doesn't go on the chip itself. The chip is more like a processor that can like process memory built in with like a hardware controller that can actually turn pins on and off, but the memory lives on a flash chip. And I think that's this little black dot right here. It's tricky to see. So there's the actual chip itself, and I think that black dot is the memory. So I'm gonna have to figure that out at some point, but I do know that that is one of the things that kind of happens behind the scenes. It has to be a quad SPI flash, but I haven't tested any of this yet. I wonder if that shows up in the pinout here. No, they probably don't break out those pins now I'm thinking about it. There's probably not a one-to-one mapping of the microcontroller to the outer pins. That makes sense. Okay. So I guess I'm happy with Python. I mean, that was pretty straightforward. I'm sure I could keep following through this and figure things out on my own pretty easily. I guess what's next? So I'm wondering if there is. All right, that was a quick tutorial. I'm wondering if there is a quick setup guide in C. There's the DigiKey video. I'm not going to watch a video on a video, though. How to program it using C. Yeah, sure, we'll take a peek at this link here. So in order to do this, we're not going to, I'm assuming there's already some firmware on here. So like someone probably wrote in C a Python interpreter, and that's what MicroPython is probably written in. And then that lives on the actual microcontroller, and then everything that we're sending to it, we're just putting it in memory and it's interpreting it on the fly. Whereas if we're going to do this, it's almost going to be like in the same way that we updated the firmware on this. That's probably the process that we're going to have to take to push our C code onto it. So we'll have to compile it and everything. So let's see. Even though the Pi Foundation promotes Python as the primary programming language, things are quite different when it comes to microcontrollers. You know, I was not expecting the Python to be up and running that easily, so I'm trying out C, and then I'll figure out if that makes sense to use it long term or not. Which computer to use? You can use any of the Linux, Windows, or Mac base as a host. That's cool. Get the Pico's C SDK and examples. Okay. This is the stuff I like. So let's get a terminal up here. I'm in my pictures folder. Let's go to my root directory. Let's create a folder called Pico, cd into Pico, and type in ls. And I've got this little playground of a folder here. Oh, you can't see again. My bad. Thank you for calling that out. All right, so not that it matters. I didn't do anything. I'm going to zoom in here so we can actually read what's on my screen a little bit better. Let's clear that so we can see. So I just created a folder called Pico, and let's see where this takes us. Oh, they literally mk directory Pico, cd into Pico. Oh, I did the exact same thing. Okay, download the C SDK. So it looks like we're grabbing something from the Raspberry Pi official foundation, which is cool. I like using the official stuff. I've already got Git installed on my Mac, so I should just be able to type in git clone. I don't even remember what -b is. Branch, I guess. Download the master branch. So if I do this, it's probably going to create another folder. If I type in ls, yep, there it is. So that's the Pico SDK. And I always like to pull up the repositories on these. So like this is github.com/Raspberry Pi/Pico SDK. So I'm just going to grab that without the .git and just pop that open in a web browser. I like to just kind of like see what's going on over here. So this is kind of the GitHub version of what's going on in there, and we can like read the README. So it looks like they gave us a README. I could probably figure it out with just this without even following that guy's tutorial. I'm almost tempted to do that because this is the official Raspberry Pi Foundation stuff. So like anytime they're going to make changes, they will probably make it to this repository, whereas whoever wrote this tutorial, it might become out of date, but I'll follow it as this was the first one that came up. So yeah, now we have a new folder called Pico SDK. Before proceeding with the downloading examples, you have to initialize the tiny USB submodule. Tiny USB. Alright, in the Pico SDK for the USB related functions. Like, so CDC, I think that's like a CDC serial is I remember working on something where I had like a host, and I think this is just like a protocol for sending serial data over. So I'm just gonna Google that real quick. Oh, communications device class. Yeah, so there's like different classes of USB of like what it is. So like a mouse is a thing called HID, a human interface device, and then a CDC would be a communications device class saying like, hey, this is just a device that's supposed to communicate with the computer. USB is kind of disgusting to drill into in detail though. So let me go back to the tutorial. So in order for, so basically we have to somehow initialize tiny USB submodule, whatever that is, in the Pico SDK to basically allow it to act like, to allow it to do basically serial over USB. So in the Pico SDK directory, initialize the submodule using these commands. Okay, so we got to go into the folder, git submodule update --init. Just curious, I'm going to type in ls. Wow. Oh, I'm not even in the right folder. cd Pico SDK. Okay, there we go. So I'm going to clear my screen here and just show what's on here. So inside of the Pico SDK folder is making this for using Cmake. Got Cmake in here. We got docs, external lib. So it's Pico SDK init.cmake. So I've only used git submodule a few times, and I usually see that when there's a library written for different like microcontrollers, and they'll have you download the like the firmware for only the microcontroller you care about. So like if you're making something that can work with STM microcontrollers or I don't know, PIC microcontrollers and all of that, and there's like tens of thousands of different options or whatever, then it's not like downloading the firmware for every single one. So that submodule will usually reach out to an external repository and download that, but I'm used to specifying that. You usually have to type in like git submodule and then like you say what you want to download, but I don't know what this is going to do, so I'm just going to do it. Update. What the heck is that? --init. I'm going to assume that's --init. Okay, so it found the submodule tiny USB even though I didn't say it, and it looks like this is coming from, as expected, a different repository. So this is coming from something from Hathach, I don't know. I'm going to go see who wrote this. before I just start pushing code all willy-nilly to my microcontroller. So yeah, an open source cross-platform USB stack for embedded systems. So it looks like this isn't even made for the Raspberry Pi Pico, it's just the Raspberry Pi Pico is compatible with it. So it looks like this stack supports all of these microcontrollers. Okay, so this is just something generic. I haven't used this before. So tiny USB is what we're looking at here. All right, so we did that. Download some examples. The Raspberry Pi Foundation created a bunch of different examples like GPIO, so turning pins on and off, analog to digital converter, pulse width modulation for like analog write, I2C, SPI. That's cool. So instead of writing C programs from scratch, we can make use of these examples to get familiar. I like examples because it's easier to get something up and running and then figure it out afterwards. To whoever asked what my background is, it's just the Mac default background. I'm lazy and not creative. Okay, so CD ... So now it's taking me back to my my folder. This is what it said to go. So this is where the repositories that we just downloaded for the Pico. So it looks like we're going to grab some examples and we'll put that in a folder right next to our actual firmware, which is weird. We downloaded it, but we didn't really do anything with it. So this is also from the official Raspberry Pi Foundation, so I like to see stuff like that. So if I type in, let me clear my screen. If I type in ls, we see two folders here, Pico examples and Pico SDK. So Pico examples is what we just created. Installing the tool chain. Oh boy, I really hope I don't have to do all of this. All right, so we just downloaded the C source files for Pico. Oh, one other thing I'm mentioning, I'm doing this on a Mac and it will work very similar if you're doing it on Linux, but if you're doing this from like Windows, then you can, like one of the easy ways that you can do it is you can either download Git and you can have a Git terminal, but you can also like somewhere in here, if you can click download, like this little drop down. So if you're on the repository page, you just click on the drop down and then hit like download zip and it will download the zip file, which just has everything inside of it. So you can do that too. If you use the command line tool, it just is a automated way of downloading it. All right. So now sudo apt update. So I don't think apt works at all on this computer. I don't know. I guess. Oh no, yeah, unable to locate, because that's a Linux thing. So I'm going to do sudo apt install. All right. So these are all the things that it wants to install, and I probably have a lot of these in here already because I've used my computer to program. So sudo apt install, and I'm just going to kind of like copy this. Let me do Notepad, text edit or something. Just paste this in here. So we've got sudo apt install, and we're going to basically be installing all of these things. These are all the programs. I'm going to make this bigger. So we're going to install Cmake, the compiler for ARM, lib new lib arm none. So I don't know, it's a library for ARM microcontrollers. And build essentials is actually, I believe, a group of things which will be like compilers and other miscellaneous things. So we could do this all in one go by typing sudo apt install and then kind of like having a space separated like they had there, or we could do it one at a time. So I'm just going to do it one at a time. Sudo, oh, it's not apt for me. I have to use like, I don't know, brew, I think is what it is for Mac. Install Cmake, but I should already have Cmake installed on here. Running homebrew as, oh yeah, I forgot I'm on Mac. I don't need to do sudo, so we'll just do brew install Cmake. And then it has to update every single time. There's also another thing I believe called Mac ports, which I've had to use occasionally because they both pull software from different places. This is taking its sweet old time. You know, the part that is going to annoy me if I have to download it this way is I know this is a pretty big download here, and this is part of the STM32 Cube IDE, so like I already have Cube IDE installed since I already do all my STM stuff, but I'll probably just end up downloading it again because I think this is like packaged in with the compiler. I know, I know, I'm reading some of the comments. I have to move my face around occasionally. I don't know, I'll have to go back and check afterwards. Yeah, Homebrew is like the package manager of Mac. Yeah, it's like one of them, and you have to do something weird to install it as well. It's like not an official one, it's kind of like a third-party thing. This is the one that's kind of most common I'm seeing. Man, this is taking its sweet old time though to update. Because this will do it automatically, whereas like usually on Linux you have to run this command here to update. Say, hey, I want everything updated. But this one kind of just does it every single time you run the command, which I don't know. Maybe that's good, maybe it's bad. Whoa, what is all of this? Are these all my updates? I don't have that much stuff on here. Gotta scroll all the way to the top. Here we go. Updated, so new. So I guess it just like updated lists for all of these programs. I certainly don't have this many things installed on, so this is, oh wow, there's stuff happening. I'm not touching anything. So I guess it just listed a bunch of options that were available. Okay, so I guess I didn't have Cmake in here. I should be able to type in Cmake now, and it should. Yeah, so it's a valid program. It's saying, like, hey, if you want to use Cmake, this is how you got to do it. Well, I have Cmake now. So let's take a look. The next one is this. Oh, I'm not looking forward to this. So we're going to do brew install gcc, oops, gcc arm none EABI. I don't even know what none and EABI are, but they're just always there. Uh-oh, so yeah, this is where there's no formula available with Homebrew for me, so I think I have to use Mac ports, which I think is Mac port. Uh-oh, we might be hitting a brick wall here. Ask the internet for help. Mac install ARM ABI, whatever. To install. So yeah, port. So it is port. Do I not have port on here? Okay, well I guess I don't have port. I thought I had it at one point in time. Because yeah, I've noticed that like Brew is like the easiest one to work with in terms of like support, but like some things just don't exist there. So I'm gonna install Mac ports here. I think I have. Let me check which version I have about here. I have Catalina, so gotta download this. Oh no. Yes, I would like to keep this file. Yes, I know I can harm. So while this is going, so Homebrew, does Pi Pico come with a bootable or onboard programmer? I'm not sure yet. So I do know that the Pico has direct USB support. So what would really matter is how the bootloader is set to work. Because like usually what you have to do is somehow you have to communicate from your computer to the chip itself. And things like the Arduino, all their bootloaders are over things like serial or something. So if you want to push data to it, you need to talk to it over like serial or SPI or some other protocol that it actually supports. But this one I think has like native USB support, so there's like actual pins, and I'm gonna verify this real. Actually, you know what? Let me get to a download and then I'll come back to this because this is gonna be a long download. I do want to read the license. Oh, this is a short license. Okay, that was straightforward. I thought I had this. I probably removed it because I was probably running low on space. Speaking of, how am I doing on space? I have 12 gig of free space, running kind of short. I discovered the hard way that you can't just add more space to your Mac. You can't just get a bigger hard drive in it because they're fused directly to the motherboard. Okay, so while this is going, let's look at the actual RP2040 data sheet. So I don't know, I'll find some like Mouser. RP2040. Raspberry Pi, RPI chip. Why don't these look normal? Can I sort by pricing? Where's the $1 ones? $1.25. Alright, this is probably it. This first one. Let's see if I can read that data sheet. Yeah, they always make them look so pretty. Alright, so I'm going to go to like pinout, zoom in a lot and move this out so it's not by my face. Raspberry Pi Pico pin out. So that's actually, I don't want the Pico pin out because like I want to see. Oh, this is a data sheet for the Raspberry Pi Pico. Pico is their name for the breakout board, but I want like the actual RP2040 data sheet. I want the microcontroller itself. Let's try this one. RP2040, there we go. Now let's search for pinout. Pinout reference. There we go. So that's the chip I was showing earlier for anyone else that just popped in. The actual brains behind the operation. That little guy right there. So on the back we've got all of the pins, and now we're trying to figure out what they do. So I do know like these QSPI, slave select, SD1, SD2, SD0, SC clock, and SD3, all of those are used to communicate with the flash module that's on there, because that's this doesn't hold any of the memory, so it has to load it from an external chip, and it does that over quad SPI, which is the same as SPI, except instead of having one data line, it's actually got 4. So that's what SD 1, 2, 0, and 3 are. It's an interesting order for them to be. But it just lets you transmit things 4 times as fast, because this chip runs pretty quick. But what we're looking for is any USB. I see USB VDD, so that's probably the power coming from the USB port. We got USB DP and DM. I'm not super familiar with USB the actual protocol and how it works. I've got like a very high level understanding. But I do know that typically you just need this is the Pico. How did I end up back here? But I do know you only need like 2 lines of data for communication with it. So like a standard USB port will have basically power, ground, and then 2 lines of communication. I usually see them called like D plus and D minus or something like that. So, oh, that's what DP stands for, D plus and D minus. Okay, so they just did like the letter M instead of like an actual plus or minus. So these pins are probably like this little group of them right here are probably where you can communicate over the bootloader. So I'm going to take a quick peek here as well, because I want to learn as well how this thing works for bootloaders. Bootloader. All right. Chapter 1, Introduction.
There's a couple out there that are good.
Let's see. A UF2 bootloader in ROM. I don't know what that is.
Wait, on this thing.
Yeah, there's some
Dual core processor. Alright, that's not what I want. X in and X out. So yeah, it does mention the USB bootloader here, and it says that it requires a 12 megahertz crystal. So whatever that is, or 12. So if we're gonna program it over USB, it looks like we absolutely need to have a 12 megahertz external oscillator, which is interesting. Or crystal, not oscillator. Extract the second stage bootloader from external flash. Huh, so that's interesting. Oh, I guess that makes sense. So that's just kind of, it sounds like if it can't access the USB bootloader or whatever the primary was, I'm assuming it's USB, then it's just going to start reading data from the flash chip, which I guess makes sense. So I probably wouldn't even call that really a bootloader. I would assume that just executes the code, whatever is on there. Boot ROM. The boot ROM size is limited to 16 kilobytes. So ROM is read-only memory, which means that you can't change whatever the boot ROM is. That's the stuff factory put onto it. There are 2 cores on this, so I guess that makes sense. We kind of have 2 brains behind the operation. So there is an initial boot sequence, whatever that means. Processor core 1 has a low power, wait, and launch protocol. So it sounds like core 0 is probably what's kind of getting everything kicked off, and then processor core 1 is probably the faster core that you don't want booting up until you're ready for it. Looks like USB MSC class compliant bootloader with UF2. I'll have to search what that is in a second. But that's the bootloader for USB. So it's got a built-in ROM that allows you to download code or data to flash or RAM. So the chip itself does have onboard RAM. The only difference is if we were to put code onto the RAM, it would disappear when we kill power and restart it. Whereas if we have flash, an external flash chip, that will survive reboots. The USB Pico bootloader. So apparently we have a MSC class compliant UF2 support, whatever that is, and it looks like they have another type of bootloader. They got a lot of bootloaders on this. Pico bootloader interface for advanced management. All right, so that's something interesting. Routines for programming and manipulating the external flash. Okay, that. Oh, so this is all still stuff that's in the boot ROM section. So they have basically hard-coded code, actually physically there, never changeable for changing the flash. Fast floating point library. So there's basically code that we can access that's read-only that they already gave us for manipulating floating point numbers, because typically microcontrollers will be really good at integers and stuff, but not floats. Stuff for fast bit counting and manipulation, fast memory fill. Okay. Oh, wow. So I guess this is what happens here. Both cores enter the boot ROM, so they're both doing that. Which core am I? So if it's core 1, it just goes to sleep. Core 0 will go to the POR rescue flag set. So I guess there's a rescue flag. We'll just assume no. The watchdog boot to SRAM set. So watchdog is like typically for causing your processor to reboot if you ever lock up or something like that. So maybe you accidentally ended up in an infinite loop and you want to like kill it after a second or something. So it looks like this has the ability to detect whether or not it was rebooted naturally or because of a watchdog. Then there's a 100 microsecond delay. Well, this is, I can't even read this. There we go. A 100 microsecond delay. And then it reads the flash CSN chip select. So that's okay. So then there's read flash CSN, whatever. I don't know if that's the chip select. It looks like if whatever that pin is high, it's going to boot from flash memory, and if it's low, it's going to boot from USB. Okay. So I guess that answers that question. Is I'm assuming that's what that button is that's on here. That boot button. So if we press that button, it probably is pulling this line low, which means, hey, boot from the USB protocol instead of from flash memory. And if we don't press it, it's probably high and probably going just through the standard flash boot. Okay, so there's a lot of stuff going on in there. So whatever this turns into is a USB device, which comes from here, starts the crystal oscillator, and then it kind of like works its way down here and eventually ends up in USB device mode boot code. So I don't really know what the difference is between the USB Pico bootloader interface and this MSC class compliant bootloader, but hopefully we'll figure that out soon enough. Alright, so this is done downloading. Let's get port install. Let's get the ARM framework in here, GCC ARM. Oops. What? What did I do? Oh, I probably have to restart the terminal window. Port. Hey, alright, that works. I don't know, exit. How do I get out of here? Exit. Okay, cool. So we'll do CD into Pico. CD, well, I guess it doesn't really matter where I'm executing this. I'm just kind of installing stuff. So we'll do port, install, GCC, ARM, none, EABI. Insufficient privileges. I am not allowed to unless I use sudo. Cool. That doesn't work. Did I do a typo? EABI. Alright. Back to the internet. Oh, weird. So they took it and they renamed it. This is why I like to do things one at a time instead of just getting one giant error code for all of those things. So to look at what they're doing, this is what that website told us to do, and in order for me to do it on Mac ports, I have to install. They called the program instead of this. They kind of renamed it to ARM none EABI GCC. Okay, so let's try this. Sudo port install that. See, now this I kind of expect to be big. I don't know if I can see how big it is on this, but typically compilers are not small. So I guess we've got whatever this is. I might as well search for this while this is running here because it probably has a different name too if I had to guess. So we'll just search for this. And I'll search for Mac because I'm going to install with a Mac. Also a program, if you're trying to install this stuff, because installing your development environment is going to be different for Windows and everything. If you're doing it with Windows, there's a problem called Cygwin, which is like that, and it lets you install Linux-based build development tools, and it's very similar to how Git Bash works, and you can install stuff in a little terminal window. I'll jump back over here. This is fancy, little dots moving. Okay, well, let's see. New lib arm none EABI. That's what we got to install somehow. I don't even see anything about that. What is this? C library and math library compiled for bare metal using Cortex ARM. Newlib, so I guess this thing is called Newlib, whatever it is a C library and math library intended for use on embedded systems. Okay, so that sounds pretty necessary. Because if we're going to do any code, we're probably going to reference whatever comes in this new lib. And it looks like it's specific for just any ARM processor, not just the Pico here. Uh-oh, alright. The following dependencies will be installed. So it looks like it's actually, by installing the normal compiler, we're getting some bin utils, get text. We're getting a bunch of other stuff. So yeah, I'll hit yes to continue on here. Oh yeah, if I was on a Mac M1, that would not be fun. I'm afraid of them. I've heard there's a lot of problems with dealing with this kind of a thing. This is crazy. I mean, I got the Blink working in like 30 seconds using MicroPython, and this is taking like installations and dependencies and all that to get it working in C. The only reason I'm pursuing this a little bit is because one of the projects I need to do is kind of like squeezing every little bit of performance out of this chip. And I don't really know how fast this is running in MicroPython, but I do know that we're not just executing code. Instead, we're like reading code and then interpreting it, and then somewhere that interpreter is executing actual machine code to carry out the tasks. So I'll be doing some SPI communication, and it needs to be, I don't know, I guess the SPI is kind of the limiting factor for the data throughput here. There's a ton of stuff in here. Yeah, it kills me to watch this happen because I know I have it already installed. I think I have it like, whatever, I'll get to it some other time. I'm gonna check how much disk usage I'm using. I was at 12 gig and now I'm at 8 and it's dropping. That is sad. I'll have to find somewhere that I can put this long term. Well, I guess I'm going to move this out of the way. I don't need to look at the Pico anymore, so I'll move that out of here. Oops, that's not what I wanted. This is what I want. I'm going to set that up there, and I'm just going to keep reading through the datasheet a little bit and see if I can find anything interesting out of here. And, you know, I totally closed it. I remember closing it. RP2040 datasheet. I want to read about whatever UF2 support is. So this says, oh, it's taking me to a Microsoft UF2. Huh. I don't think I've ever downloaded something from Microsoft's GitHub. USB flashing format. UF2 is a file format developed by Microsoft, known as Make code, that is for flashing microcontrollers over MSC, mass storage class, aka removable flash drive. Okay, so I did see that then. So let me go back to here. This is all my devices on here. My guess is if I, oh no, of course I moved my image out of the way. Let's bring this guy back up top. If I were to unplug this, press that button and hold it, which should cause it to boot to USB mode, and plug this in, yeah, look at that. It shows up as a removable device right here. Look at that. Oh, look at that. There's already a website on here. Index.htm. What do we got? Redirecting to raspberrypi.com. Okay, so it looks like it comes with, it's acting like a flash drive here. And then there's, this just forwards us to raspberrypi.com, I guess. And this tells us, oh, look at that. No, I don't want it. It's locked. Can't, cancel? Can I just ignore it? Yeah, I'm gonna ignore it. No, I just want to read it. Well, I can't zoom in. I'm just gonna duplicate it, whatever. I'll zoom in on this one. So this txt file says UF2 bootloader version 1.0, calls itself a Raspberry Pi RP2. RP2. I guess is that like a shorthand for RP2040? Board ID RPI RP2. What's the RP1? Okay. So that's cool. So it does show up as a USB flash drive. So like, if this works how I'm expecting it, usually what you can do is you can just take your compiled version of the code and just drag and drop it into here, and as soon as it detects that there's a hex file or like ELF or binary or whatnot, then like it should copy it to flash memory. I think that's how that works. That's kind of cool because like I guess we just need to compile it and then drag and drop it. That's actually a really sweet way, and that's all built in too. That's not like we had to go, because I know you can get stuff like this for Arduino as well, but like you are putting that in as a custom bootloader, but this is like hardware on there. That's cool. I like this. All right, how are we doing over here? Still going. Alright, so back to this drive. Oh, you know what? I just saw something in there in my echoic memory here. The UF2 file consists of 512 byte blocks. Each is self-contained, independent. Each contains magic numbers. Okay, I was just curious what this actually did. So this is probably like the format for transferring stuff, a UF2 file. Yeah, this is over my head here, so I'll just pretend I didn't see it. We'll go back to this. So these are all the pin descriptions. There's the bootloader, boot ROM. Oh wow, so they got like an actual write-up of the flowchart. That flowchart was very nice though. Watchdog boot allows them to install their own boot handlers and divert control away from the moon's on the. That's really cool. So like we can make different code that will execute when we recover from a watchdog. So like if we wanted to record something, be like, hey, I need to store how many times we crash basically. That would be this. It's kind of like a blue screen recovery. Flash boot sequence, one of the main challenges. Uh-oh, I don't want to hear challenges. What do we got here? One of the main challenges of a warm flash boot is forcing the external flash. So we've got an external chip from XIP mode, whatever that means. Oh, XIP is execute in place, meaning that we're just going to like load data from the chip, just literally execute it without copying it, I guess. Change it from XIP mode to a mode where it will accept standard SPI communications. One of the main challenges of a warm flash boot is forcing the external flash to a spot where it will execute SPI commands. You know, I feel like it always does. I have a flash chip around here somewhere, and I want to see what that means. So, like, does that mean that when it boots up, it's ready to just execute code and that we can't send it SPI commands? Because I'm pretty sure you send it an SPI command to allow it to accept SPI commands or something. There is no standard method to discontinue it on an unknown flash, because like this is allowing us to, it's kind of standardized to read data, I would assume, but not to exit that. So it looks like the boot ROM provides best effort sequence with broad compatibility. So depending on what chip it is, it looks like it's gonna do one of these four things here. CSN equals 1. We saw CSN earlier, which I thought was that button that's physically on there, the boot button. IO30 is this. So it's gonna, so it looks like it's gonna change input output pins 0 through 3. Is that right? Where's our, I don't know. There's IO pins 0 to 3 are all zeros, pulled down to avoid contention. And then it waits, I would assume, 32 clock cycles. Then it's going to change chip select to 0. Oh yeah, chip select is the chip select pin for the flash. Chip select 0, meaning enable it. So we disable it. This is kind of just the safe set. Disable it and set all of these pins to 0. So these are probably the 4 communication pins. We enable it and set all of them to 1s. And it's done with pull-ups instead of like hard setting it, so that way it's not forcing it high or forcing it low. It's just kind of like lightly tossing it up. So that way if there's a short circuit or a pin that's trying to be forced, it's not gonna, I guess, contention, they're not gonna fight over it. Issue 32 more clocks. So we're enabling it, and then we disable it, and then we enable it, and then we send apparently this over MOSI, master out, slave in. So we're transmitting, is that one? Oh, I see, 1 byte of binary 1. So we're just sending the number 1 over MOSI, or just over the standard SPI output here. Driven low Z, all other IOs high Z. So that's the impedance. So this is driven, this is actually driven. So it's not just doing this over a pull up or pull down. But all of the other ones are high impedance, so basically floating points. And then it does 16 clocks. Okay, this is designed to miss the execute and place continuous codes on Cypress, Micron, and wind bond parts. If the device is already in SPI mode, it interprets this in sequence as basically 2 no-op instructions. Okay, so that's pretty cool. So if the device is set to execute in place, that should, for these brands here, it will force it into SPI mode. But if it's already in SPI mode, these basically are interpreted as no-op instructions or do-nothing instructions, which should be ignored. Okay. As this is best effort only, there may be some devices which still remain in execute in place mode. There are then 2 options. So we can use the less efficient XIP mode, where each transfer has an SPI instruction prefix. So I'm assuming that that's more overhead, but it seems like even if we're in execute in place mode, we can still send data, is what I hear that as. It's just slower. Boot code installs. Man, I see this one being an issue. I'm anticipating a lot of Reddit posts about people asking why something is running like really slow. Boot code installs compatible execute in place execute sequence in SRAM. So in RAM memory, the boot code installs an exit sequence in SRAM. So the RAM memory, configures watchdogs such to more. My brain is not working enough to interpret that sentence. After issuing the exit sequence, the boot ROM attempts to read the second stage. Yeah, I'm just going to ignore that one as well. Okay, flash second stage. So that was what? Flash boot sequence, and then flash second stage. So that boot is kind of what gets the flash chip ready to go, I guess. And then the second one must configure the SSI and external flash for the best possible execute in place performance. So all of this is just happening, it sounds like, just automatically based on code that's flashed to the chip itself, and it's trying to figure out how to set it up to work at maximum performance. This includes interface with the interface width. Oh, you can. Does that mean that it doesn't have to be a quad SPI? Could it just be a single SPI chip? The frequency, SPI instruction prefix. I don't know what that is. And the execute in place continuation code for address data only modes. Huh. To the SSI, yeah, this is getting a little deep here. This is getting into checksums, like how data is moving across. Okay, well, I have a feeling I'm going to spend a lot of time in here when I actually build my own board, and I probably will boot it up, and it's probably just going to not work. And then I'm going to have to figure out why. So I'll come back into this section, figure out what's going on. You know what I'm going to do real quick while this is running? So I'm going to go RP2040, I don't know, Pico C boot, or like flash LED X download. I'm going to see if I can find somebody else's like pre-compiled, I don't know what I'm typing in. I want to find like a program that's pre-compiled that I can try and just drag and drop to see if I can get it to blink. How to blink an LED with Raspberry Pi on Pico and C. I wonder. Oh, this is on. Oh, this is like an article. I want to see if I can find somebody else's hex file and just steal it, and then try that while I'm waiting for my compilers to download. Raspberry Raspberry Pi Pico hex download.
It's like kind of close.
Could really get
we
anything
have
on here.
tolerance set by John, but he doesn't like his own tolerance.
Pi
that he
Pico
wants.
example.
Because if it's like, if I have a couple perfect.
I don't know why
ones
anyone
that
would actually
match,
upload their compiled
then there's
version
one that's
instead of
like
source
this,
code, so
14.96.
I'm probably searching in
He'll get
vain.
upset
Oops, that's a
because
data
it's
sheet.
not 14.09 if I
Raspberry Pi Pico examples on GitHub. Blink.
we could send our addresses to get
Yes, this is
posted
just going to be the
online.
C code. And I think, yeah, this is already, I already have this whole thing downloaded in here. I just can't compile it. How's our compiler running? Still going. Wow, this is not fun.
So this one is just 1.1, and then we changed it for ourselves to 0.05 because our rigs were differently.
I wish I could do more than one at a time, but I don't want to risk this one getting hurt. How's my computer, what's it called? Disk usage. Utility. How am I doing? Okay, still got 8.5 gig. We're still good.
If I get
Man, this is a massive download.
So now it's all good, right? Okay, so now you do.
All right, I'm gonna read through and see how much of this I can just memorize as we go along. So we're stuck at this line of code here because we're still downloading all the stuff. Oh, look at this warning. This is a very large installation, which applies like 2 gig of disk space. Make sure you have enough disk space. Yeah. All right. Cool. I might try this on a Raspberry Pi one of these days. Although I can't even seem to get my hands on them, so I'd have to go pull one from a different project.
It doesn't stay higher.
Yeah, we'll grab a cup of coffee and relax.
So this is where.
I think he meant to say read the data sheet and relax.
So let me go back to for.
For an answer of am I doing more content? Yes, I will do more content. I'm probably going to pick up with STM32 again because I want to do some SPI stuff. I got some cool hardware that people have been sending me, and I want to make some videos on it, but I'm still waiting on permission to like do stuff, like for one, say who it is, and two, what I'm going to be working with. But I've been playing around with a lot of stuff, and I've had a lot more experience now than I have since I made that last video in getting projects working, as well as the chip shortage forcing me to like change a lot of microcontrollers just because the existing ones weren't available. So I'll probably touch on stuff like that. I do plan on starting to put some time in on weekends again to make some more videos. Anyway, let's see, the first C program, so they've got a blink code. Oh yeah, I do want to look through that while we're waiting here. Here you can see the blink code. You can use any editor like Vim. That's a dangerous recommendation if you're not familiar with Vim. Do they tell you how to exit Vim? They probably don't. No, they don't. That's a sick joke. Alright, well if you haven't used Vim, it's like infamous for being difficult to get out of. There's another program called Nano, which is a little bit more straightforward, more like a normal text editor. But I'm going to use Vim because I like Vim a lot. So if I go to my Pico folder that I had, type in ls, I've got my 2 folders. Let's go into the Pico examples. Let's make this a little bit bigger so we can read it easier. Oh, actually, I gotta go like this. Come on. There we go. Let's see what folders are in here. We have all of these folders. Let's look at the blink example. So cd blink, type in ls. And then Vim is the program, blink.c. And I'm just going to say this now. The reason that people don't know how to exit out of this is because it's not very self-explanatory. If you hit any button, like if you hit I, for example, it puts you into insert mode down here. And then you're kind of like, you're in normal typing mode, but if you're stuck there. But if you want to quit, you have to hit escape, and escape will take you out of that mode. And then you type in the very intuitive way to exit, which is :Q. That's what you do. These are where commands go. Commands go down here, and then you hit enter, and then it yells at you because I typed stuff in up here, and it's like, hey, you didn't save this. Are you sure you don't want to save it? So I have to type in :Q exclamation to mean yes. I mean it. quit. I don't care if you're saved or not. So if you're using Vim, that's what you need to remember. And if you did want to save it, it's if I like type stuff in up here, you have to hit escape :WQ, which means write and quit, and then it saves it. Now if I go back into that file, it should have my garbly-goop up here. So I'm not going to show you guys how to use Vim. Very fun if you want to learn how to use it. It's a very powerful text editor if you're stuck in a terminal like this and you don't have like a mouse and a keyboard or something. So if you're doing like communication over like Serial or something and you have access to a terminal, it's pretty powerful to learn. But anyway, so it looks like they're including this thing called pico/standardlib.h. So what I'm going to do is actually undo all of this. I think there's a way where you can split. So v split. This is testing my Vim knowledge here. Let's just do a dummy file. So I've got a split file, and I think you can type in exclamation mark in here as a command and like execute an actual command in here. So I'm going to type in ls. Okay, well that's not what I wanted to do, but that's fine. I did want to come back and look at this. So they've got something called Pico. Where was Pico?
This is like the address
I don't see Pico. I see Pico board and PIO. Huh. Let's jump back into here. Let's quit out of one of these. So they're referencing something called Pico standardlib.h. I don't know where that's actually installed. ls. All right, so we're in that folder. Let's go back out of folder. ls. Yeah, I don't know what they're referencing here. Huh. Let's go out another folder. Let's go into the, it's probably referencing this, the Pico SDK, which is what we installed first. cd Pico SDK.
Yeah.
cd pico. I'm still in the Pico examples folder. cd cd Pico SDK. Let's see. So now there should be a folder. It's probably in the lib folder or something like that, or source. I don't know. cd lib. Tiny USB. Okay, let's go out of folder. Let's try the source file. I just like to peruse through these and see if anything looks familiar in here. Boards, RP2040. Okay, I think we're going down a little rabbit hole that we don't need to. So I'll just back out of this and go back into the examples. CD into the blink folder again. Then blink.c. So I guess somewhere when we're doing the framework, they created this standardlib.h, which is kind of like a standard library for all C functions. I don't actually know what they put in their standard library, so that's kind of why I wanted to hunt it down, but it's probably nothing. I don't expect to read anything here that I don't understand. Okay, so every C program starts with int main, like this, and then they have preprocessor commands in here where they say, if not defined, Pico default LED pin, then we throw a warning. We say, warning, blink example requires a board with a regular LED. So somewhere, probably in some like board configuration, they have a statement in there that says something like, I don't know, it's going to be like, define Pico default LED pin, and I think it was like 27 or something like that. So some line of code like this probably exists, probably either in like the Pico framework or whatnot. So, and if it's not, it's going to yell at us, and it's going to be like, hey, we'll still compile it, but it's going to print out this message. So yeah, we got a constant unsigned integer. They're calling it LED pin. Using all uppercase letters for this. Interesting. And then usually I see most people will, well, I guess it is a const as well. They'll usually use all caps like this with underscores when you're doing defined statements, but I guess a const uint is very similar to a defined statement in the way that it actually gets used. So they're creating LED pin. Oh, this is kind of funny. They're just saying equals Pico default LED pin. So they could have just, they didn't even need to do this. They could have just used this in here. So they're using GPIO init, and they're initializing the pin. That probably sets it to like, I don't know what the init does. We'd have to see what that code actually does. I was assuming it would set it as an input or output, but it looks like that's the next line of code here. It probably like enables, if I remember from like other microcontrollers, there's sometimes like clock pins, like, or to enable the like peripheral clock. So like you can't even use it until you enable the clock, and the clocks are all off by default to save processing power and battery life or whatnot. So they're off, and then this probably like turns it on and enables it or something. And then we've got set directions. We're saying I want you to set this pin to a GPIO out. This is very similar to how STM32 code looks. While true, we're going to go into an infinite loop. GPIO put. So we're going to, I guess, put a 1 onto this pin. Sleep for milliseconds, 250. So these are all kind of the commands that are different. So like in Arduino, it wouldn't be called GPIO put. It would be like digital write. And then sleep milliseconds would be delay. So we'll have to kind of find those words. And then for like STM32, those are like, it's like HAL, GPIO, write, pin, I think. So something like this would do it in STM32, but it looks like this is a little bit cleaner, I guess. So sleep is pretty self-explanatory. I mean, this looks great. I mean, if I can just get this to compile and run, this is exactly what I'm going for. And it's actually really cool that if I quit out of this, that they've got, let me go back one directory, they've got examples for all of these things, and this is their official examples too. So ADC, blink, clocks, Cmake, divider, DMA. This is incredible, because like that's always the hardest part, is finding an example that works. So like I care about SPI. I want to just peek at what that looks like. Oh boy, here we go. All right, so we have BME 280 SPI, MPU 9250 SPI, SPI DMA, and SPI flash. So my guess is that, and I'm actually facing this with my video for the next one, and that's one of the reasons that I got held up on this, is teaching SPI is fine, but like what do you talk to? What device is another SPI device? Do you talk to another microcontroller that's set up as an SPI slave, or do you talk to like a temperature sensor or a flash memory module or who knows what? So my guess is that BME 280 is probably some sort of a sensor if I search it. And that's probably code that they gave us as an example for how to communicate with that. Yeah, look at this. It's a humidity sensor. So BME 280 is a humidity sensor. So, sure, yeah, you know what? Humidity sensor sounds fine. I don't want to do this. So this code would be how to communicate with a humidity sensor. MPU 9250, what's this? Is this an accelerometer? Yep, 9-axis motion tracking device. Cool, so there's an accelerometer. So they give examples of those. Let's look at the humidity sensor. That sounds simple. So CD BME 280 SPI. So they've got their C code. What is this? They've got a PNG. Oh, look at that. They've got like a README for this. So my guess is we're reading this like this, and it's kind of ugly and hard to read. I don't even know what an FZZ file is. But if we were to do this through GitHub, we would probably get pictures and stuff. Let's see, where were we? Let's just go to github.com/Raspberry Pi. It was like /RP or Pico examples. There we go. So I wanted to check out the SPI. Oh yeah. So BME 280. There we go. Yeah. So the README is now rendering. So that .adoc file, which is here, I guess I could read that through the terminal, but this has all my nice formatting and stuff like that, so we can actually read it. So look at that. This example code shows how to, this is super cool. It can be interfaced with I2C or SPI. So we're using SPI and working at 3.3 volts. So they tell you how to wire it up. So it looks like there's these pins. We got MISO, which is master in. chip select to say which device we're using, the clock pin, master out, that's our data output, power, and ground. That is standard SPI stuff. This example is using SPI port 0, and I think there are a handful of SPI ports on this guy here. Let's take a look at this in the bigger tab here. So there's probably more than one SPI. Yeah, so we see SPI 0 RX. Oh, it's interesting that they call it RX and TX. That's weird. I don't like that. I like Mosi and Miso, but hey, maybe that's the new thing. All right, so we've got channel 0. Do we see SPI 1? Yep, there we go, SPI 1. So like we could probably communicate all of these pins look like they're SPI 1 with different like buses, different SPI buses. So it looks like it's got 2 buses. I saw SPI 0 and SPI 1. That's cool. So yeah, that's just, I guess, the code. So this right here, this file is, look at that, fritzing. That's probably the FZZ file. Or it's the PNG. Oh, you know what that is? They probably gave us the source for this or something. I've never used fritzing. But that's probably what this file is right here, is probably the layout. And then this PNG file is probably, can I do this? BME 280 SPI bb.png. Does that work? Look at that. Yeah, so that's that image. They just had that stuck in there. So it makes more sense if you view it on the GitHub preview. But it looks like this is the only file, so let's take a peek at it. Vim BME 280. Yeah, that looks good. All right, so now this is a little bit more complex. This is a standard C library for I/O stuff, doing string manipulation as well as standard C. And then this is Pico specific. There's standard lib, so this probably has all the like pin and GPIO stuff. And then here, this is interesting. Pico binary info.h. I have no idea what that is. Now it looks like they have a hardware thing, which is probably for the Pico as well, specifically for communicating with SPI. And they probably do that because you don't want to have all of the code to deal with all of the peripherals all the time for every project, even if you're not using it. Oh man, they documented even this. This is the same thing that we saw earlier on how to wire it up. This is probably just for communication. They usually set things like this right here is 80 in hex would be, I don't know, let's write this out. So 8 would be, so this would be a, that right there is a 1, this is a 2, this is a 4, so this would be an 8. So that right, this 80 in hex basically translates to 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. This number here. So it would be like a 1 in the, whoa, what did I do there? In the, there's 8, 9, 10, 11, 12th spot, or the 11th bit would be a 1. So that's probably used for some kind of communication for reading or writing from this sensor. Oh, these are some disgusting variable names. Let's see if they make sense. Dig T1, dig T2, dig T3, and they're all different data types. One's unsigned, this is int, that is signed, this is another unsigned int. So we got T1, P1, so maybe temperature 1, P1, I don't know what that is. H, humidity maybe? Okay. Yeah, this is always overwhelming to look at all this. Following compensation functions are required to convert raw ADC data from the chip to something usable. So I guess there's a built-in analog to digital converter on the chip or something like that. Each chip has a different set of compensation parameters. So compensate temp. Oh my gosh, this is gross to look at. So they're taking, oh, okay. So there's like ADCT, so it looks like we're passing in an ADC value, which would be the raw 32-bit number, and they've got some very descriptive names here for these variables, var1, var2, and t, but it looks like they're bit shifting this one over 3 minus This number bit shifted left 1. Okay, yeah, I'm sure if we read the data sheet on the actual humidity sensor, this would make sense. None of this is SPI specific though. This is probably just for converting the temperature. So I'm not going to look at this too much. Pressure. Oh, so that value, the P up here that I didn't know what it was. We've got T1, we've got pressure and humidity. So temp, pressure, and humidity. Sounds like a little cool sensor. Compensate pressure and compensate humidity. Wow, this is gross. Okay. CS select, chip select. Assembly. All right, so they're doing assembly code in here. So if you haven't seen this before, C code gets compiled into machine code, and machine code has a one-to-one relationship with assembly. So like no-op, for example, is an assembly code that will directly translate to a binary number, which means do nothing. So if you were to maybe do like in C, if you did like a delay function, that delay function might just call a bunch of no-ops. That's one way to implement it. It's a bad way, but it's one way to implement it. So here we're just explicitly calling in, when you say ASM and then volatile, we're explicitly putting in assembly code inside of our C code. Volatile means don't optimize this away. The reason it needs to be here is because when our C compiler comes in here and it tries to optimize it, it's going to see 3 no-op instructions, and it's going to be like, hey, I could speed this up by getting rid of these 3 no-op instructions because they do nothing. But with microcontrollers, you sometimes need those in there to kill time. That being said, it's really weird that they're doing it three times. It's like a very arbitrary amount. Then we've got GPIO put. So this is how we write to a pin. We're writing to the chip select 0. So this is like a mini delay. It's like a 3 clock cycle delay. And then we write 0 to the chip select pin to enable it. And then we do 3 more delays. That is really weird that they're doing it like this. I guess it's fast. I don't know where they came up with 3. And it looks like chip select deselect, so to disable the device, they're doing the exact same thing, but they're setting the pin high, which means disable. Yeah, I'm surprised this is an example. It looks like it's written by a completely different person, actually. I wonder if it says at the top. No, they didn't put an author at the top. It feels like it's a very different person. They like put a lot of effort into the blink example, and it's very readable and very cute and concise. And then this one's just like, hey, I hope you understand SPI because I'm not going to explain it. But yes, this was kind of making me scared for my next STM32 video because I need to make this stuff understandable. Write register. So a lot of SPI devices will like read and write. They act like a giant memory device, even though it like is a sensor or something. It just kind of like stores its sensor value in memory somewhere, and then you just read from that memory address. So this is probably to write to it, so you can like write to a special memory address which will configure it. They're probably just sending stuff in here, but I do care about how they're actually doing it, so I want to see this. So they create a 2-byte integer, and it looks like they're in the first byte they're putting the register address and whatever 7F means. I don't really care. And then the second byte is data. So now this is what I really want to see. Okay, cool. This is what I was looking for. Chip select. So they're enabling the SPI device. They're writing with a blocking command. So write blocking usually would mean that we're going to execute this, and the processor is going to do absolutely nothing until we're done executing this code. So if we're talking about efficiency, you want to probably use like a non-blocking command, so that way your processor can go back to doing other things while this SPI command is taking place. But with a blocking, it's usually easier for debugging because it's going to execute this line of code, then this line of code, then this line of code, and everything is going to make sense, and it's going to like kill time until that's done. So our SPI default. So it looks like this is once again, very similar to how STM32 is working. We've got this SPI write blocking command. SPI default is the first argument that they pass in. Then they pass in the buffer, and then they pass in 2. So 2 is probably the length of the buffer. SPI default is probably which SPI channel to use. So it's probably like 0 or 1. So I'm actually going to go hunt for this. So I'm going to search for SPI_default.
I thought you.
It'll last.
Yeah, so it looks like it's in a.
Oh, it'll last the sun.
Oh, that's so weird that they have a define statement that's lowercase here. So SPI default is probably a 0, but it looks like this statement here says if it's not defined, so if somewhere in the microcontroller thing it's not defined, then we are going to, or, oh man, if any of these are not defined.
Run it one more time.
If any of those aren't defined, then it's gonna yell at us and it's gonna be like, hey, you need to define these things. Okay, so that's interesting. So SPI default is probably somewhere else.
Yes, Dad. Dad.
Here's a pro tip.
That's how Alex was like, mine's 150.
So let's see. Yeah, that's that. I do want to look this up
You're
though.
right.
It's like where my mom's like, here's some money for a fridge.
Yes.
Yeah, you don't say no, you say
Thanks.
thanks.
Hardware SPI. So let's see if I can find the way that this works.
I know it's beneficial.
SPI right blocking. Yeah, so it's an instance to the SPI instance. So it's actually not a number. It's a pointer to the SPI instance. So we probably can't just type in a number there. But then this is the actual data, and this is the length of the data. Okay, so that makes sense. I wonder where you get something. There's SPI default is probably port 0, but I don't know what the rest of it is.
Yeah, but then you didn't use it for how long?
He couldn't. It was my fault.
Oh.
You can get a great lease on a
Read
Nissan Versa.
registers. So yeah, this is going to do that same thing. So we've got
Dude, the Versa whips.
SPI write blocking. We've got
Price is 14
that here again, right? Because when you read a register, you write a command. You say, "Hey, I'm going to read from you at this address," and then you actually read the data over it. But there is, I wonder if they do read write, because technically SPI is full duplex, meaning that you can send and receive data at the exact same time since you have two separate wires.
So messed up.
Dude, $280 a month.
I hope this is not too loud in the background that I'm in. Everybody's getting kind of lively,
For a 2021 Nissan Versa.
but they're having a good time, so I'm not going to say anything.
That does seem like
But yeah, I do want to check. We did find this right here. So it looks like we got SPI write blocking, read blocking.
I would just put it on my
Oh, right here. And write read blocking. So yeah, if you do this, you can probably read and write at the exact same time, which is kind of sweet.
What is the cheapest car?
All right, well, I mean, this is really what I was looking for, because this gives you the ability to do just about anything. Looks like they've got also some commands in here for reading and writing 16-bit numbers instead of 8-bit numbers too.
Looks like it though.
So yeah, this is cool. I like this, and it looks like I'm just perusing through here, and it looks like we've got the ability to check if something's busy. So I'm assuming this is for non-blocking calls that we can check whether or not it's done. So there's probably in here how we have read write blocking. We probably have up here is like SPI read or SPI write. No? Is that not a thing? SPI says slave, SPI writable, readable, busy, blocking. Yeah, I don't see any non-blocking stuff. Probably have to. They probably don't have APIs for that, or probably different. It's probably like in advanced or something. I'm fine with blocking for now. Well, it has been close to 2 hours. It's been an hour and 45 minutes here. This thing is still cruising, so I was really hoping I would be able to get more done, but I think I'm just going to wrap up this stream. I got to jump to some other things, so thanks for everybody who is watching live and everyone who's looking afterwards. I'm probably not going to simplify this because I'm not going to make a Raspberry Pi series or anything like that anytime soon, because I'm still learning it for the first time and I don't want to be spewing nonsense until I know what I'm talking about. But if you did like this, let me know, because I could do more live streams like this in the future. It seems like it'd be boring to watch somebody else learn something for the first time, but hey, that's not my call. So I will talk to you eventually. See you guys.
As long as you go around the road.